All right, so let's go. Let's review. Recall. Review. So Q is a quadratic form, binary quadratic form. Ax squared plus bxy plus cy squared. The basic question is which numbers are represented. And we observed that it's enough to ask about primitive representation. So this is just representation. And then maybe a better question is which n are represented primitively with x and y coprime, i.e. primitively. And as you saw, you can take a single form. There was this duality between taking a single form and changing x and y, or keeping x and y to be 0 and 1 and changing the forms around. So we saw that there's an equivalence relation. There's an equivalence, which is that Q1 is equivalent to Q2 if and only if. And again, you can speak about wider senses of equivalence than this, but let's say if there exists a matrix, 2 by 2 matrix, with determinant 1, you could allow determinant plus or minus 1 if you want, since we're taking all integers, but let's think about this slightly more restricted notion, narrow sense. So two forms are equivalent if there exists a matrix such that Q1 is equal to Q2 composed with gamma. Okay, which means matrix multiplication on xy. Great. So, is there a way? So, given a form, given a form Q, we get the equivalence class of Q. This is the equivalence class of Q. Equivalence. In other words, just group all quadratic forms according to their by this equivalence, up to equivalence. Equivalence class of Q, which formally is the set of all quadratic forms Q prime, which are equivalent to Q. So this seems like I mean, it is an infinite set. It's a countably infinite set. It's a pretty big set, but it's not such a scary thing to try to understand. In particular, there is a way of finding a good representative. So our goal for today is to understand equivalence classes, by finding good representatives, by finding, well, this is the reduction theory of binary quadratic forms, by finding a reduced representative. So let's see what we mean by that, or how this kind of thing could go. Where was our quadratic form from last time? Does anybody remember what it was? Was it definite or indefinite? This goes slightly differently for definite versus indefinite forms. 7, negative 11, 15, and it is 11 squared minus 4 times 20. It's definite, right? It's definite. Yep. Great. So let's do that one. So let's as usual understand it by example. So example, we have our Q0 is 7, negative 11, 5. It's a nice form. Yukong, you wanted to say something? No? Change your mind? No? Still typing? Can this be the norm form? That's a good question. So there's only so we can consider the problem in a ring. We'll find out. Very shortly. Yeah, we'll find out very shortly. There's a sense in which the answer is yes, and there's a sense in which the answer is probably not. Let's look at the discriminant, and then I can tell you. Right. So you guys are all going in the right direction. So this is Q0. What's the discriminant? So the discriminant of Q0, I'll just write D for now, and maybe Q0 I'll write as Q. This is the guy that we're working with. So I have 121, B squared minus 4AC. That's 20 times 7, 140. The discriminant is negative 19. Discriminant is negative 19. Okay. So this form is definite or indefinite? Can you guys write in? Great. Thank you, Sriya. Definite. All right. Now remember, we can turn the form into a quadratic polynomial. Cheek. Why is it definite? The discriminant is negative. So a negative discriminant means it only takes positive or negative values, and this one only takes positive values. So only represents positive numbers. Only takes positive, well, non-negative values. And in fact, it can only be 0 at 0, 0. Okay? So we start with a binary quadratic form, and we turn it into a polynomial in a single variable by restricting to y equals 1. Restricted to y equals 1 gives us this polynomial, quadratic polynomial instead of quadratic form. And this polynomial, so this is some parabola. The graph of this thing is some parabola. And the parabola, so there's the graph of the parabola. We know that the parabola does not cross the origin. That's what this discriminant being positive means. Whatever the parabola looks like, it does not cross the origin. So no real roots. No real roots. This is the graph. Y equals, or f of x equals, whatever. I guess I could call it q of x1. Y equals f of x. Okay? No real roots. And so what? Well, it has complex roots. So the roots are, what is it? Let's call them alpha. Alpha q, alpha plus minus q. There are two roots. And it's b, it's negative b, right? Negative b plus or minus square root of the discriminant over 2, I guess it's capital B, over 2a. That's what it is for a general quadratic form. In our particular quadratic form, negative 11 is positive 11, give or take. Square root of the discriminant is negative 19. Negative 19 all over 2 times a is 14. Okay? So where is this number as a complex, in the complex plane? 11 over 14 is close to 1. It's like, maybe this is 1 and this is a half. So 11 over 14 is between a half and 1 somewhere. And then root 19, well, it's bigger than 4 because root 16 is 4. So it's like a little bit more than 4. 4 over 14, what is that, about a third-ish? So if this is 1 and this is a half and maybe this is a third. So the numbers are right about there. Does that make sense? For our alpha? So this is alpha plus, and its complex conjugate is alpha minus. So we have these two complex roots, two non-real roots. Does everybody see that? So it's real part, this is the real part, and about 4 over 14 is the imaginary part. And they have the same real parts and they have opposite imaginary parts. Okay? These are our two real roots. Our two roots, non-real roots. Okay, now we found equivalent quadratic forms. And let's see what happens when you find an equivalent quadratic form. So there's an equivalent quadratic form, equivalent form. For example, we took Q0, let's call this Q1. Q1 was Q0 composed with, I don't know, was this one of the ones that we looked at? Actually, let's do this. Let's do this. This might be, no, actually this might be good. I think this might be good. I think that might be good. So this is 1011. Right. Any questions so far? Everybody's following along? We're doing some, this is high school mathematics at the moment. So if anything is confusing, please stop me. That's an equivalent form. I don't remember what this form was. Does anybody actually remember what this form was? Or should we work it out again? It takes a second. Let's work it out again. So what does this mean? This means that Q1 of xy is Q0 of, well, let's just work it out from scratch. So I have Q0 of x, I guess. And then instead of y, I have x plus y. Right? And it's easy enough to go back into what Q was. So this is 7x squared minus 11 x times x plus y plus 5 x plus y squared. And we could use the general formula that we worked out for how this works in general, but let's just do it right now a little bit quickly. So I have a plus 5x squared, I have a plus 7x squared, and I have a minus 11x squared. 5 plus 7, 12 minus 11 is 1, x squared. How about xy's? I get a minus 11xy here, and I get a plus 10xy there. So this was a plus xy. I hope you guys are checking my calculations and making sure I'm not making a mistake. And how about a y squared? There's no y squared here. The only y squared is there, so plus 5y squared. Negative xy? Let's see. Yes, negative 11 plus 10 is a negative. Thank you very much. Thanks, Dipendra. Okay, so that's the form. So Q1 is the equivalent form 1, negative 1, 5. Okay? And let's see what has happened to the roots. So these were the roots for Q0. I'll call them alpha 0 and alpha minus 0. So what are the roots? Now you can see. What are the roots? What are the roots of Q1? So take 10 seconds, 30 seconds, whatever you need. Compute the roots of Q1. In other words, set y equals to 1. What are the roots of this polynomial? And when you have the answer, just say, got it, in the chat. And when enough people have written got it, that's how I know to go on. Does everyone know what they're supposed to be working on? Is anyone just totally stuck and doesn't even know where to get started? Can you write in stuck? Got it. Great. Great. Okay. Fantastic. All right, so everyone who's got it, why don't you tell me what the roots are, and hopefully you all are typing the same answer, and I don't have to do the calculation. So the roots, alpha plus minus 4q1, are awesome. Awesome. Great. Everybody's getting the same answer. Let me see if I agree with you. Negative b is plus 1, plus or minus square root of the discriminant. Now I have b squared is 1 minus 4 times this. That's negative 19. Curious. Negative 19. That's curious, isn't it? Divided by 2a, which is 2. So where is this number in the complex plane? This number, let's draw it in the same plane. This number has real part a half. That's easy. Real part is a half. And the imaginary part, this is again about 4. 4 over 2 is about 2. So it's about here. Here's alpha 1 plus. And all the way down here is alpha 1 minus. Does everybody see that? And look at the coefficients. What do you think is a simpler quadratic form? 1, negative 1, 5, or 7, negative 11, 5? What do you think we should call the simpler form, the reduced form? Yeah, exactly. The later one is simpler. So Q1 is simpler than Q0. So let's make a few observations. So Q1 is more reduced than Q0. And the question is, can we reduce Q1 farther? Can we reduce Q1 even farther? Further, farther? Same thing. All right. Now, before we go on, this is curious. Is this a fluke that we got the same discriminant, negative 19? What do you guys think? Probably not. It's a good guess. We should prove this. This is a very beautiful theorem. Beautiful theorem. If two quadratic forms are equivalent, then their discriminants are related by yes, are related by equality. Okay. Now, yes, Karen? Were you going to say something? No. Nope, still typing. Nothing. Okay. Great. In fact, this is a good theorem to prove because it'll take us... there's a variety of ways of doing this. So let me say exercise. Do this completely directly. Daniel? Not yet. We don't yet have a definition of more reduced. We're just kind of looking at it, but we're working our way towards a definition and a reduction algorithm and a proof. But I realized that we didn't prove this yet, and this is fundamentally important. So let's do it. So if two quadratic forms are equivalent, their discriminants are indeed the same. And let's prove it. So exercise. Prove this directly from algebra. Do this directly from algebra. So we had that formula, A1 is equal to something involving A's and B's and C's and so on, and the original A and A2 and A3, A2, B1 and C1. Or were these C2s? Anyway, we had this algebra for what the new thing was. We had this, we worked out all this algebra, and so the new discriminant is B1 squared minus 4 times A1 C1. And how does that relate to the original? Factor all of that, and it's kind of a mess, but worth doing if you feel like it. I'm going to give you a better proof, I think. Well, once I give you the better proof, maybe you don't want to do the exercise anymore, especially since I sold it as annoying algebra. But it can be done completely directly from algebra. I want to go into what Dipendro asked about last time, which was what does this have to do with matrices? So a better proof, in my biased opinion, is to make a few observations. So here's another observation. If Q is equal to ABC, that is ax squared plus bxy plus cy squared, what is its half-Hessian matrix? It's half-Hessian. Most people call this a Gram matrix. Gram matrix. What do I mean by a half-Hessian? Well, what's the Hessian? In general, if you have a function of two variables, say, the Hessian matrix, what people do often is they just abuse notation and give it the same letter. Will you guys be bothered if I give the same letter to a quadratic form as a matrix corresponding to that quadratic form? You'll allow me to abuse notation? Sarah, Sheik, Dipendro. Might be confusing. As long as you don't get confused. Right. Alright, fine. I won't call it that. What should I call it? I'll call it the matrix M. Although I like to use M for other things. But alright, too late. I'll call it M. Okay? The half-Hessian matrix. The matrix version of the quadratic form. So what does that mean? Well, it's the half-Hessian, so it's half of the matrix of partial derivatives. So this is partial derivatives, well, d delta I delta j. Okay, what is that? That's half of, what is two derivatives in x? What happens when I take two derivatives in x? Here. Here I get, the first derivative brings down a 2a x to the 1. A second derivative is just 2a. Beautiful. 2a. How about two derivatives here in x? One derivative in x gives a by. A second derivative, what's the derivative of by with respect to x? 0. And how about here? There's no x's, so this is 0. Great. So that was two derivatives in x. How about derivatives in x and then derivative in y? So if I take a derivative in x here and a derivative in y, I get Are those new zeros or were those the original zeros? Yes, I get 0 again. Okay, that's a new 0. How about if I take a derivative in x and then a derivative in y here? I get b. And differentiating is symmetric in whether you do it in x and then y, or in y and then x, at least for now. And how about two derivatives in y brings down a factor of c, 2c. And so half of the Hessian matrix is the matrix, it's a symmetric matrix, by just taking A and C and half of the diagonal entries. The off diagonal is half of the middle entry. Okay? Are we basically putting the B in half and keeping the A and C? That's exactly what we're doing. That's exactly what we're doing. And this is a symmetric matrix. Notice that this is a symmetric matrix. All right. This is a symmetric matrix. What is the determinant of this matrix? Yes, almost. It's A times C minus a quarter B squared, also known as negative a quarter times B squared minus 4AC, also known as negative a quarter times the discriminant. Okay? That's the determinant of the matrix. And now, what is Q of xy? I claim Q of xy is m times xy times xy. Let's see if that's true. So here I have xy. The matrix is A, B over 2, B over 2, C, xy. So m is also sometimes called the quadratic product, because you don't have to put the same xy here. It becomes an inner product. Anyway, never mind that. So what is this? What does this come out to? Ax plus b over 2y, ax plus b over 2y. And what does the bottom come out to? B over 2x plus cy. And now I want to take that and multiply it by the row vector xy. Well, that's just the dot product of these two things. So I get ax squared plus b over 2xy plus b over 2x times y plus cy squared. Does everybody see that? Q of xy. So if I did that a little too fast, just do, let's make this an exercise for you to check on your own, even though I've done it for you. But okay, does that make sense?
Where did you use the row vector?
Where did I use the row vector? So I have a row vector and a column vector. And I first did this multiplication to get a new column vector. And then I'm matrix multiplying this row vector by this column vector, which is just a dot product. So it's first term times top term, second term times bottom term.
Alright. And where did the Hessian matrix, where did you get the idea to use the Hessian matrix?
Right. Where did it come from? Well, it came basically from this observation. Okay? So a quadratic form, you can take any quadratic form. This is a general fact. Let me say remark. This is a general fact. Here's a quadratic form in 4 variables. 7x squared minus 5xz plus 3yw minus, I said minus w squared minus z squared. Okay, here's a random matrix. Here's a random quadratic form. I want to realize this quadratic form as the product of x, y, z, w times a matrix times x, y, z, w. And it's very easy to read off how to do this with a factor of 1/2. So the diagonal entries will be 7. Is there a y squared term? There's no y squared. Is there a z squared term? There's a negative 1 z squared. Is there a w squared term? There's a 1 w squared. Does everybody see what I'm doing? And how about an xy term? No xy term. How about an xz term? Yes, negative 5 xz. So I have to give half of that to the off diagonal, negative 5 halves, negative 5 halves. How about an xw? No xw, 0, 0. How about a yz? No yz. How about a yw? What am I putting in the yw slot? Almost 3. Karen? It would be 3 if I didn't take the half-Hessian. 3 halves, right? Karen, is that what you were going to say? Yeah, it's because there's a 3 here, and if I want to make it symmetric, I could put a 3 here and a 0 here, but I want a symmetric matrix that that has the same, that recognizes this thing as an inner product. And what is this term going to be? What is this term going to be? Yeah, I changed it. Sorry, Devendra. Exactly, Karen. -1 and -1. Okay? So you see how you can turn a quadratic form always into a bilinear product of a symmetric matrix? So this is just a general fact. And so now I can actually put an equal sign. These two things are literally equal. This, when you multiply it all out, this is a 1 by 4. This is 4 by 4, and this is 4 by 1. And so the 4 by 1s, these cancel and these cancel, so I get a 1 by 1. I just get a scalar. Where did the 7 come from? The 7 came from x squared. So the diagonal entries you just literally put in, and the off-diagonal entries you put in with halves, and you put it in 2 places. Sarah, does that make sense? Whoops, Sarah got disconnected. All right, when she comes back, I'll ask that question again. Okay, so this is a general fact, a general product of quadratic forms. I mean, this is somehow why things like general relativity work, or in general, so quadratic forms, Riemannian structures, they all work because they can be realized as linear algebra or bilinear algebra. These bilinear structures are really fundamental in very much mathematics. Dipendra, you wanted to ask something? No. Okay. So, given this exercise, what happens? Let's see. My kids wrote on this one. What happens if right, let me hide this remark. Is that the rank? The rank of the quadratic form, the rank of this, okay, thanks, sorry for dropping out of the call. No worries. Hopefully that made sense. Sheik, the rank, when you have a matrix, you can compute the eigenvalues of the matrix, and the rank is how many non-zero eigenvalues are there. So these symmetric matrices, one of the reasons it's nice to use symmetric matrices are always diagonalizable. So it has a nice Jordan normal form, if you guys remember what that is from linear algebra. But I'm not going to be using that right now. So if you don't know what I just said, you should know, but let me not judge or whatever. It's okay if you don't know. If you don't remember. You learned it at some point, but it's okay if you don't remember. I'm not using anything serious about linear algebra right now. Okay, so check this out. Check out what happens. So if I have a quadratic form that's equal to, if I have Q2 that's Q1 composed with a matrix, right? I.e. they're equivalent, i.e. Q1 is equivalent to Q2. How would I write this in the language of matrices? Then the matrix M2, well, what does it mean? So let's do this at xy. So this is M2 of xy, also known as Q2 of xy. And that's the same as Q1, but now I'm going to replace xy by gamma xy. I mean, I'm sort of abusing notation here. I'm writing this as a column vector so that I can act by gamma, and here I'm writing as a row vector. So really, I mean sort of as a column vector here. So you should think of this, what Q2 does is it takes xy as a column vector and puts the transpose on the other side. So that's this bilinear structure. Okay, does that make sense? Now what is this? This, well, Q1 of anything is M1 of that thing on the left and the transpose of that thing on the right. So this is M1 of gamma xy and gamma xy transpose. Is anyone with me? No, I lost you, Ray. So where, let's see. Are you happy with writing Q2 of xy as M2 of xy and M2 of xy? Let me do this, let me write this, let me replace this by xy transpose. Maybe that'll make it a little bit more clear. So I have the column vector xy transpose. The transpose is just the row vector. Okay? So Q2 takes a, if you like, column vector, and it makes it, sorry, Q2 takes a row vector, makes it a column vector. Let's be careful. Let's make Q's take column vectors. So this is not a column vector. This is a row. One of these days I will say the right words at the right time. This is a row vector. It's a horizontal. Horizontals are row vectors and verticals are column vectors. Let's say Q's take row vectors. What Q does to a row vector, now this is not a row vector, so I have to take its transpose. Okay, to make it a row vector. Does that make sense? So what Q1 does to this vector, the same as what it does here, I could make this much simpler. All right, too late. Is it takes the transpose and then puts it over here. So let's do an example. Okay, let's do an example so that you see this in action. For example, we have the Q0, which was 7, negative 11, 5, is similar to Q1, which was 1, negative 1, 1, negative 1, 5. Oh, Sheik, you're asking how did I get the 4x4 matrix? So you just read it off of the entries. You just read it off from what entries, what things have an x squared. Is there a y squared term? This is the x squared term, y squared term, z squared, w squared. And then the off diagonals are the cross terms. The xy, the xz, the xw, xy, xz, xw, yz, yw, and zw. And you put them, to make it a symmetric matrix, you take half of the coefficient and put it there twice. Okay? Try this. Let's call this an exercise if I went a little too fast here. Okay, so Ray, I'm going to try to convince you of what I'm saying up here. So this is this quadratic form. This is this quadratic form. In other words, Q0 of xy is equal to xy times the matrix 7, 5, negative 11 halves, 11 halves, negative 11 halves, times xy. Maybe a better way to say this is you leave this xy and here you put x comma y transpose. All right, that's what Q0 is. What's Q1? Q1 of xy takes any entry xy and does this to it. Up. What am I going to put here? What's this term? I just want to read directly from the ABC what goes in the half-Hessian, what goes in the Gram matrix. Yes, thank you, Ray. And how about the 2-2 entry? 5, yes. And Sheik sees the negative a halves on the off diagonals. Perfect. Everybody sees that, right? Great. Now, what does it mean that Q1, let's see, Q1 was Q1 of XY is Q0 of this matrix. Now, the way I've written it is not so good because I'm sort of mixing metaphors. I'm saying take this matrix and act on XY, but this is going to give me a column vector, whereas what I'm taking is row vectors. So let's put a transpose here. That makes this into a column vector, a row vector. It's almost comical. Whenever I say column or row, just flip them. I mean the opposite of what I say. Anyway, you know what I mean. I hope you know what I mean. Now, great. Well, let's write out what this is. This is Q0 of, what is the transpose? What happens to matrices when you multiply them and take the transpose? You guys know this fact? If you take A, B transpose, that's A transpose, B transpose, right? Yeah, they switch. Exactly, Detendra. They switch. Okay? So these also switch. So xy as a column vector transpose is xy as a row vector. And then this thing gets transposed. Now I'll just write it. I won't write out what the transpose is. I'll keep the t there. So this is a new row vector. And what Q0 does to a row vector is it leaves that row vector there. This is xy times this thing. That's this row vector. This is what Q0 does to any xy, so that's what it does to this xy. Okay? Times the half-Hessian, times the Gram matrix of Q0. 7, negative 11 halves, negative 11 halves 5. Times the transpose of what was in here. And the transpose of what was in here was the original thing. 1, 0, 1, 1, xy. Does everybody see that? So look back at what I was trying to mumble up here in the general case. If a Q2 is Q1 composed with gamma, that means, let's write it again like this, xy, m, xy, this is m2. So that's, and what is Q1? Of course, Q1, as we already said, is xy times its matrix, its half-Hessian. Okay, so Q1 is this thing. That's also Q0 of this, which is all of this stuff. So what does that mean in general? So I'm using Q0 and Q1 here, but Q2 and Q1 there. Gosh. I hope you guys are still okay with all the annoying little changes. xy m2 xy is equal to, let's write this out a little bit more like this. The transpose of this, again, is xy gamma transpose m1 gamma xy. Which is exactly what I have down here. I have xy gamma transpose m1 gamma xy. Does everybody see that? Great. Great. So from this formula, it's immediate. So in other words, so this was our sort of explicit example, our aside. From this formula, so these things are the same as matrices. So as matrices, since they're the same as quadratic forms, and the quadratic forms determine the matrices, as matrices, the matrix M2 is equal to the matrix gamma transpose M1 gamma. Okay? And let's take determinants on both sides. Determinant of M2 is the determinant of gamma transpose M1 gamma. And what do you know about determinants of products of matrices? Yep, it's the product of the determinants, right? Yeah, so this is the determinant of gamma transpose times the determinant of M1 times the determinant of gamma. Ah, but what was the determinant of gamma? Yes, the determinant of gamma, the definition of gamma, gamma was in SL2Z. And these are all things of determinant 1. How about gamma transpose? Same. Okay, so the two matrices have the same determinant. Determinant of M2 is equal to the determinant of M1. But wait a second, what's the determinant of the gram matrix? How does that compare to the discriminant of the quadratic form? This was negative 1/4 times the discriminant of the first form. And this is negative 1/4 times the discriminant of the second form. So the discriminants, so Q1 is equivalent to Q2 implies the discriminant of Q1 is equal to the discriminant of Q2. Okay? Which was the theorem we were trying to prove way up here. So one more time, if two things are equivalent, then their discriminants are equal. This is either a directly algebraic calculation, or if you're willing to pay the price of thinking about things in terms of linear algebra or bilinear algebra, bilinear forms, instead of quadratic forms, so quadratic forms determine bilinear forms, then what you see is that this composition, what it does on the level of the matrices is it's not conjugation, it's multiplying by gamma on one side and gamma transpose, not gamma inverse on the other side. But either way, it fixes the determinants. Fixes the determinants, and the determinants are immediately relatable to the discriminants. So the discriminants are fixed. Okay? Does that make sense? Can I have a make sense, or I'm kind of confused but keep going, or I'm totally confused, please slow down? Okay, thumbs up. Thumbs up. Okay, great. Here's a question. Is there a converse to this? Does discriminant of Q1 equal to discriminant of Q2 imply that the two things are the same? I'll give away a little bit of the punchline. This happens only if there's unique factorization in the ring of integers of square root of d. So, in which case, this can be realized as a norm form. So this goes all the way back to Yukong's question. So the question is this true in square root of minus 19? I don't remember off the top of my head if 19 has class number 1 or not. Let's find out. Let's find out. Yukong? Do equivalent forms have the same eigenvalues? Well, they have the same... Yeah, that's a good question. The answer in general should be no. And yeah, the answer is no, because the eigenvalues are very close. You know, you can work out what the okay. Let's follow your question, actually. Let's work out what the eigenvalues are. Okay. Yeah, so the answer in general, no, but this is a fascinating direction to pursue. So no, but sometimes yes. And this is, I'm opening Pandora's box to topics that we surely won't have time to go into. Well, maybe it depends on how quickly I can go. Okay, so Yukong's question, does Q1 equivalent to Q2 imply eigenvalues of M1 equal to those of M2? Right? Do equivalent forms have the same eigenvalue of their gram matrices? So let's work out what the eigenvalues are. If M is the matrix A, B over 2, B over 2, C, what are its eigenvalues? What are its eigenvalues? This is a very quick computation. It'll be two numbers whose product is -1/4 times the discriminant. Yeah, it's going to take us... Can I do this quickly? Do you mind if I do this quickly? All right, let's just do it quickly. So you look at the determinant of m minus lambda times the identity and set that equal to 0. So this is a minus lambda, b over 2, b over 2, c minus lambda. So what happens here, the determinant, so this is the determinant, I get an AC, I get a minus a plus c lambda, and I get a plus lambda squared, and then a minus b squared over 4. So the thing to notice is that, so I get a lambda squared, and I get a minus the trace of m, minus the trace of m times lambda, and AC minus b squared over 4 is the determinant of m. So plus the determinant of m. Equals 0, and now I can apply the quadratic formula. Lambda is equal to negative b, so this is the trace of m, plus or minus square root of the discriminant, which is b squared trace of m squared minus 4 times the determinant, all over 2. Okay, so that immediately tells you that the answer to this is no, since this part is already different. The traces change. The trace changes. Okay? Since the trace is a plus c, which is the trace of m, changes. I mean, we can see it already on our two quadratic forms here. A plus c here is 12, a plus c here is 6. So the eigenvalues are different. So the eigenvalues are not the same, but the products of the eigenvalues, which you can see here, when I multiply this out, I get trace squared, so those cancel, and then I'm left with a determinant. So those will be the same. So eigenvalues are not fixed, but discriminants are. What about eigenvectors? Well, once the eigenvalues are not fixed, yeah, so neither are the eigenvectors. You can work out what the eigenvectors are, and they'll similarly depend on the trace. Okay. Neither are eigenvectors. So the matrices are not similar. They would be similar. Okay, let's go back. Here's why you're thinking about eigenvalues and eigenvectors. If I had an M1 gamma M1 inverse instead of transpose, right? Then the two matrices are similar in the sense of a conjugate. So you conjugate a matrix, a lot of these things get preserved, but this is just gamma times gamma transpose. The only thing that's preserved is the determinant, and that's only because the things you're multiplying by on both sides have determinant 1. Actually, if they both had determinant -1, they would cancel, the two minus signs would cancel. So that's why it's okay to work with GL instead of SL, but never mind. Okay, does that kind of make sense? So, let's circle all the way back. We have proved the theorem that if two things are equivalent, then they have the same discriminant. So we're not surprised that we're seeing this -19 here, because that was the same for Q0. Now, let's go back to reduction. So back to reduction. Back to reduction. Can we understand what has happened what happens to these roots? Let's say we have a imaginary a negative discriminant, a definite form. What happens to the roots alpha q plus minus geometrically when q is replaced by an equivalent form? When q is replaced by an equivalent form. In other words, should we have known, given where these alpha zeros are, should we have known where alpha ones would have wound up? Okay? Does the question make sense? Well, this is another kind of easy explicit calculation, which again will make, when interpreted in a matrix sense, will kind of clarify things. But let's go back to explicit calculations, just not to overburden you. So what I want to prove, I actually want to answer this question. So the total answer, which we're about to go into, and it'll take a little time to flush out the details, is discriminants being the same does not mean that the quadratic forms are in the same equivalence class, right? This is equivalent to, this is the same thing as the class of Q1 is the same as the class of Q2. So it turns out, this is a major theorem that we're about to prove. Again, it'll not immediately, it takes a little bit of time. Is that, and it'll explain the reduction theory of the quadratic forms. The theorem is that if the so when you group things by discriminants, there are only finitely many equivalence classes for any discriminant. So if that finite number is 1, if the class number is 1, if the number of classes is 1, then this is the sum times yes. Okay, and that'll be proved through the reduction theory. So let's go, and we'll see that through what the geometric action. One way of seeing that. You don't have to do it this way. This isn't how Gauss did it, but it's sort of, many people today, myself included, think a much nicer way of seeing things. Okay. What happens to the roots geometrically? Let's look at a slightly different. So we had this root. Alpha 0. Why is it finite? That's the big theorem. That's a major theorem of Gauss. The finiteness of the class number. Yeah. I'm going to write all this down. Let's go back to this picture. So here's our root alpha 0. Alpha 0 plus or minus. Let's just work with the upper half plane instead of working with, there's going to be a complex conjugate in the lower half plane. So let's take this in the upper half plane. This means the complex numbers with imaginary part positive. Okay, so I don't have to draw both pictures. I can just draw the upper half plane picture. Here's a half, here's 1, here's 1 and a half, and so I'm just thinking about alpha 0 here-ish. What was alpha 0? Where is it? It's 11 plus root 19I over 14. Okay, does everybody see that? So that was over here-ish. 11 14ths is between a half and 1, and root 19 14ths is here. So this is alpha 0. And this pen is dead. That's alpha 0. Alpha 1 corresponded to the quadratic form Q1, which we obtained from Q0 by composing with 1, 0, 1, 1. And this number was, where was it? Does anybody remember what it was? Here it is. 1, right, we know what the quadratic form is, so we can read it off. It's 1 plus or minus root 19 over 2. Alpha 1 is 1 plus, we're staying in the upper half plane, square root of 19I over 2. So that was, this is like over here somewhere. Real part equals a half. This is alpha 1. Should we have known from the beginning where alpha 1 would wind up? So this is the upper half plane. Imaginary part bigger than 0. Okay? So I want to understand the action on quadratic forms as an action on the roots. Want to understand equivalence on quadratic forms, or transformation in terms of what it does to the corresponding roots, alpha 1 versus alpha 0. Okay? Does that make sense? So let's do the calculation. Let's do the calculation. Right. So what is alpha in general? Let's say we have two quadratic forms. Let me label them the same way now. Instead of 1s and 2s. We have 0s and 1s. We have Q0, we have Q1, it's A1, B1, C1, and Q1 is Q0 composed with A, B, C, D. Okay? Alright? Then there's alpha 0. Alpha 0 is the root of this quadratic polynomial, so that's negative b1. I'll take the one in the upper half plane, so the plus sign. We're treating this as for negative discriminant, discriminant negative. There's a different story for discriminant positive, for the real roots. So this is root d, which I remind you, maybe should I write it as absolute value of d times I? So to make it kind of explicit that we have a complex number, over 2a. B0 over 2a, 0. Right? And we have alpha 1, which is a negative b1 plus square root of d over twice a1. And the question is, what do the two have to do with each other in terms of this gamma? Okay? Is the question clear? Yes, no, maybe? Yes. This should be D0 and this should be D1, right? They're the same. The discriminants are the same because of the theorem that we proved. Okay. Gosh, how do I want to do this? There's a variety of ways of doing this. I suppose we could just directly go into what B1 and A1 are. Yeah, why don't we go directly into what B1 and A1 are? Let's do this algebraically. Because some of the other, I have in mind a few other approaches, but just looking at the time, I think the fastest one, the one that's conceptually the easiest, and it's just a matter of doing the algebra, as opposed to doing something that's conceptually taxing, but then makes the algebra trivial. Right? That was kind of our point of view here. Our point of view with this theorem is, we know what A1, B1, C1 are. That takes no work. The only problem is to then do the algebra. Or we can tax our brains on something conceptual that then the proof of the theorem becomes trivial. Let's do the brute force algebra in this case. So I have to remember what these things were. Does anybody remember? A1 is easy because A1 is Q0 of AC, which is A0 A squared plus B0 AC plus C0 C squared. C is also similar, but actually there's no C in this equation, so I don't need to work out what C is. What was B1? Do we need to do it out again? Let's do it very quickly. Let's do it very quickly. So Q1 of XY, which is this A. So I'm asking what the XY component is of Q0 of AX plus BY CX plus DY. Right? And the B1 component is the XY component. So I'll have a 2AB A0 times 2AB from here. If you don't remember this formula, you can look back at our notes where we derived it. Sheik, you got the formula? So I don't have to rederive it? Ah, beautiful. 2AB times A0, B times, B0 rather, times, there's going to be a component from A times D and a component from B times C, so AD plus BC. Thank you, Sheik. And a C0 times a B squared, sorry, from this one, which is the CD. Twice CD. Beautiful. Beautiful. Thank you, Sheik. So let's look back at alpha 1. Alpha 1 is equal to negative B1 is all of this stuff. Negative B1 is negative A0 times 2AB plus B0 times AD plus BC plus C0 times CD. Okay? Plus square root of D times I all over twice A1. A1 is A0 A squared plus B0 AC plus C0 C squared. Okay? That's what A1 is. And I want to know what A1 is in terms of A0. And I claim, let's see if this is right. I claim it's either this or something very closely related to it. I claim it's A times A0 plus B over C times alpha 0 plus D. I claim that the way to get the next root from the previous one is to apply this operation. So this is going to be some massive amount of algebra. Before we do this massive amount of algebra, let's make sure I got this formula right. There's a reason this is the formula. There's a conceptual reason, which involves talking about the projective line, which is what I don't want to do in the last 5 minutes and run out of time. So I thought let's just do the computation. But let's check the computation before we do the computation. Check if this is right. we had our alpha 1. Again, in our example, check in our explicit example, alpha 1 was 1 plus root 19I over 2, and alpha 0 was 11 plus root 19I over 14. And the question is, if I apply an ABCD and gamma, ABCD was 1, 0, 1, 1. Okay, so let's check what, so I'll call this the action of gamma on alpha 0. What gamma does to alpha 0, gamma being ABCD, what it does to alpha 0 is this thing. This has a name. It's called a fractional linear transformation. Fractional linear transformation. And again, this becomes extremely natural from the point of view of projective geometry. Why fractional linear? Well, linear transformation is just to take alpha 0 and replace it by a alpha 0 plus b. And it's not that simple. It's a linear thing and another thing in a fraction involving these two linear things. So that's why it's called fractional linear transformation. Okay? Let's see what happens when we do the fractional linear transformation to alpha 0 with this gamma. So gamma composed with, or not composed with, but acted on. This is a different kind of action. I don't have another, I'm running out of symbols. Gamma acting on alpha 0 means I take 1, right? Question? Nope. I take a gamma 0 plus b, so that's 1 times alpha 0 plus b is 0, divided by c alpha 0 plus d, and that is what this transformation is. Does everybody see how I got this formula? I just took this formula, this fractional linear transformation formula, and stuck it into what gamma was in our case, and I'm about to stick in what alpha is in our case. So alpha in our case is, so it's just 1 times alpha on top, 11 plus root 19I over 14. That's the numerator. The denominator is alpha 0 plus 1. 11 plus root 19I over 14 plus 1. And my question is, does this thing indeed come out to alpha 1? I already am guessing the answer is going to be no, and what I need to do is take the transpose of gamma or the inverse of gamma. There's usually some little trickery to get from one to the other. I never remember what it is, but it doesn't matter. Let's just work out what the fractional linear transformation is in this case. In fact, I know what the right fractional linear transformation is. The correct fractional linear transformation to go from alpha 0 to alpha 1 is to shift by 1 and invert. So the correct transformation, I'm just going to cheat a little bit. The correct transformation should be to shift back by 1 and invert. So what matrix is this? 0, 0. Is that really right? Yeah. Negative 1, 1, negative 1. Okay. So, right, what is this? It's like the... Yeah, it's going to be some shuffling of the letters. Okay? So this isn't going to be quite right. It's going to be some shuffling of the letters and negating of the letters. Well, let me convince you. So this gamma isn't the right gamma. Let's not do this calculation. We have 2 minutes. Here's the calculation I want to do. I want to see what 0, negative 1, 1, negative 1. This is a nice matrix, determinant 1, right? Determinant is 1, acting on alpha 0 is. So I'll tell you how I knew that. I'll explain the geometry that tells me I know this is what needs to happen. What this matrix does is it shifts alpha 0 back by 1, and what this matrix does is it reflects it through the unit circle. And when it reflects it through the unit circle, it takes it to alpha 1. This is the magic that I'm trying to get us to discover on our own, which we can do, but let me rush a little bit, okay? Can I rush this algebra? Can I do it fast? And then we can watch the video back on slow-mo or something, or do it on our own to make sure we agree. All right, 0 times alpha, so this is 0 times alpha 0 minus 1, 1 times alpha 0 minus 1. That's just putting in A, B, C, D in the fractional linear formula. That is a negative 1 on top. On the bottom, I have alpha 0. Alpha 0 is 11 plus root 19i over 14. And now I have a minus 1. That's what I wanted to get in the bottom. Let's continue the calculation. So this won't work. Let's continue. We're going to try this instead. Try this. We're going to continue the calculation. So this is equal to negative 1 over. When I subtract 14/14, I get a negative 3 plus root 19i over 14. And dividing by a fraction is the same as multiplying by the reciprocal of the fraction. So that's negative 1 times 14 over negative 3 plus root 19i. Now I have this funny thing in the denominator. What am I going to do? I will obviously multiply top and bottom by the conjugate. What does that come out to? I hope something nice. Right, so I have a negative that's going to multiply both of these. So that gives me a positive. So I have 14 times 3 plus root 19i. That's the new numerator. All I did was bring the minus sign in here. The new denominator. Okay, 3 times 3 is 9. 9 minus root 19i squared is a plus 19. Plus 19. Interesting. Okay, what is 9? 9 plus 19 is 28. 28 on the bottom. On top, I have, and 28 is 14 times 2. On top, I have 14 times 3. Well, I have 14 times this thing. 3 plus root 19i. And so this is very close to being correct. The 14s cancel, and I get 3 plus root 19i over 2. So geometrically, we're here at 3/2. And I need to do one more translation by 1 to get down to 1/2. So there's one more thing that I was missing. When I reflect through this unit circle, I actually go over here, and then I have to do one more translation. All right. I'm out of time. I will continue this computation. I will explain what in the world I'm doing here, and how I knew that that's what matrices I had to use, and we will explain what process, what the action of the geometry is that makes this reduction kind of very easy and very obvious. So, questions?